Hello, my name is Talha. This is Fundamentals of an RC Plane, and today I'm going to try to communicate some really important ideas about stability, the lift formula, and they're not too hard, but if you can get it, it'll greatly increase your understanding of how aircraft work. So let's get into it. First, we're going to talk about the lift formula. So lift and S. So I should probably write out what this is. So this is lift in newtons is equal to 1/2 air density, velocity squared. I should point out that you could technically consider 1/2 rho v squared as dynamic pressure too, which is written as Q. So it could be QCl(S). This is another way you can write the lift formula. And then there's coefficient of lift. I'm not writing coefficient of lift out. And the wing area. So let's get started. Let's draw ourselves an airfoil. Now, what's the first thing that we see here? This is a bad airfoil. It's an ugly airfoil. I want to put it on my plane. Lift is the force that pushes an airfoil up. Then we have 1/2 air density. Air density is just, density of the air. So, these particles here. Uh, we can already begin to, use our basic algebra knowledge. If air density goes up, then lift goes up, right? So if you're flying higher and higher in the atmosphere, you might need some of these other parameters to compensate if air density is low. Next, velocity squared. The important thing to realize is this velocity is talking about, the how fast your wing, or in this case, your airfoil, is going in to the relative air, right? Let me explain. You can go in to the wind at like 22 meters per second, or the wind can come at you at 22 meters per second, right? Or, you're going forward at 20 and there's 2 meters per second of headwind, and that should add up to 22 meters per second. And all of these things have the same effect. I'm pointing this out because there was an ADC test flight yesterday, and some people were asking, well, why are we throwing it into the headwind? If we were to throw it away from the headwind, the wind would be rushing back this way. Let's say we throw it at 10 meters per second, and the wind is 5 meters per second. Well, we would probably have to subtract these, and it would give us 5 meters per second of total lift. If we threw it into the headwind, well, then that would be 15 meters per second, and that's more lift overall. You don't always want more lift. Obviously, go case by case, but right now we're trying to take off, and we want as much lift as we could get. So this velocity is talking about how much air is coming into the airfoil, right? So it's how much air is going in this direction. So obviously, we can also understand the higher the velocity, the more lift we get. Next, coefficient of lift. This coefficient of lift is how well is your airfoil generating lift at whatever angle of attack you're at, right? I say angle of attack, it can be due to a bunch of parameters. So let's talk about coefficient of lift for a second. Let's say you have an airfoil that looks like this, right? Obviously, thickness and a larger leading edge doesn't always mean it's going to be better. But typically, if you take a thin airfoil like this, the coefficient of lift at 0 angle of attack, meaning it's not, pitched up at all, is probably going to be, let's say, 0.5. Maybe for this, it's going to be 0.8. So this has a larger coefficient of lift at 0 angle of attack. Now let's just pick a standard airfoil, something in between. And let's say we were to pitch it up, right? You apply some elevator and your aircraft pitches up. Now, you're still going this way. The wind is still coming at you this way. It's all about relative wind. This is alpha, your angle of attack. Most of the time, whenever you pitch up with an aircraft, you begin generating more lift. In XFLR5, you might have seen a graph that looks like this. Coefficient of lift versus alpha. What it was talking about is the more you pitch up, the more lift you get. Think about an aircraft on the runway, right? Like a car with wings. It's going, it's going, it's going. What does it do to get off the ground? It pitches up, right? If it pitched up this much, I'd be concerned. But it pitches up and it starts generating lift this way. It's not just the reason it's going up isn't because, the engines are forcing it to go up. Yes, these engines are like that. No, it's because the engines are just pushing it forward. It's the wings that are causing a, a resultant force going up. Um, so what happens if your aircraft pitches up? The more it pitches up, the more your coefficient of lift goes up. We probably expect something like this. However, what happens if you pitch up too much? You stall, right? And XFR5 will probably just stop giving you values because it couldn't interpolate it. So this is our coefficient of lift versus alpha graph. The more you pitch up, the more lift you get. So this is kind of very obvious on the thing, but again, using our algebra intuition, coefficient of lift goes up, our lifting force goes up. And finally, wing area. So let's say we keep all these things constant. We keep these first four terms constant. Having a greater wing area means that you're generating more lift. You're generating more lift for the same velocity, for the same coefficient of lift, for the same air density. That's why, how do I say this? Let's say you have two planes and they have the same weight. Say they're both 5 kilograms, but this one has a greater wing area compared to this one, right? That means, let's go back to this. We're trying to generate a certain amount of lift and we're keeping wing area the same. Let's say we keep our angle of attack the same. Let's say the air density doesn't change. What would have to compensate? The velocity. That means as these two things go down the runway, for example, let's say we're talking about takeoff speed, this one with the larger wing area would maybe only have to go, say, 10 meters per second. This one might have to go 20 meters per second before they both generate enough lift to take off. This formula can be used in very basic ways. Let's say I wanted to use this to do what I just did, which is calculate my takeoff speed. My lift, 1/2 air density velocity squared, coefficient of lift, wing area, right? Sorry, I just reminding myself of the formula. Let's say I want to find my takeoff speed. I would do velocity equals to, what would we have in the numerator? We would have 2 times lift. Now, lift is in newtons, but your weight is probably, a mass. So let's do 2 times, let's say we have 5 kilograms times 9.81 meters per second squared. This makes it a force. And what's going to be in the denominator? Air density, coefficient of lift, and wing area. Let's just assume standard air density for this example. For our wing area, actually, we'll leave wing area as S for now. And coefficient of lift. Your coefficient of lift would be the coefficient of lift that you have at takeoff. While we recognize that, oh, I erased my little graph. We have alpha, coefficient of lift. What is your coefficient of lift at 0 angle of attack? It's not that high, right? However, that's why we have flaps. Whenever we have flaps on a airfoil, what does it do? It pops out kind of like this, right? And this increases your coefficient of lift. So with flaps, the line might look like this. Now, our coefficient of lift is even higher at 0 angle of attack, and we might have an easier time. So if you don't have flaps, obviously use whatever coefficient of lift at 0 angle of attack. So maybe it's 0.8. Maybe you have flaps and it's 1.2. But this, and put in your wing area, how much ever, it's 0.5 meters squared. That's a pretty big RC aircraft. And this would give you a certain velocity, and that would be your takeoff velocity. Let's say you're trying to find your, you can solve for anything with this, right? You can solve for how much wing area you would need for a certain speed, right? So you would just solve for S then. So this formula is very integral to getting an understanding. That's why we have that, that lovely parameter that we talk about with RC aircraft, which is wing cube loading. All it's telling you is for a certain wing area, how much, how do I word this? For a certain weight, right? How much wing area do you have? So if you're trying to carry 10 kilograms with, let's say it was normal to carry 10 kilograms with, you know, zero point 0.5 meters squared. However, you can still fly if it's zero point 0.3 meters squared. What would you have to do? You'd have to go even faster. So that's harder for a pilot to control. That's why we use wing cube loading as this parameter. It tells us our stall speed, most importantly. So your stall with a really high stall speed, a pilot would have to come in for landing really fast. I don't know why I drew this. I mean, it's going to be an aircraft, but anyways, now we understand this lift formula right here. 1/2 rho v squared times coefficient of lift times s, which is our wing area. While we're here, let's go ahead and try to understand a couple other important concepts. Right now, what I'm going to try to talk about is longitudinal and lateral stability. I think longitudinal stability is more fun, so I should talk about that first. For that, let's recognize one other thing. Right now, we're going to be looking at an aircraft from the side. Okay. Why do we have tails? Right? Like you might have been making ADC planes and you're making tails. Why does it exist? Why do we care about it? Why not just have a wing, right? What tails do is they make this entire aircraft into a little bit of a lever, right? Let's understand coefficient of moment in the most basic way. Cm versus alpha, right? We already know that alpha is our angle of attack, right? What happens when we pitch up, right? As we pitch up, look at the tail, right? Recognize that there's air everywhere, right? There's a bunch of air all around, up, above, and below. As we pitch up, the tail runs into a bunch of air, right? That means as our aircraft, pitches up, our tail goes down into a bunch of air, and it causes a force, an equal and opposite reaction that makes the aircraft, let's go back to the nose, go this way. What happens if we were to go the other way, right? If we try to pitch down, our tail runs into a bunch of air at the top, right? So let's erase these lines one more time. Our aircraft is pitching itself down. The tail sees a bunch of air as it moves up, and it forces the aircraft back down. Obviously, on the nose side, the tail would have this effect. If it's not obvious already, every time the aircraft tries to pitch down, the tail has an opposite effect on the nose of the aircraft, causing it to what? Restore itself. Where's my little thing? So every time the aircraft pitches up, the tail pushes it back down. Every time it pitches down, the tail pushes it back up. This is why your horizontal tail is so important on this balancing act. We're going to talk a little bit more about that in a second. However, let's recognize how we might want our coefficient of moment versus alpha graph to look. What is coefficient of moment? Coefficient of moment is just equal to these two lines right here. Or rather, it's equal to the force that the tail has. So let's say we try to pitch down. This red line right here, it's not red in real life. This arrow is our coefficient of moment. So in this case, it would have been like this, right? If we pitch down, our coefficient of moment is a force going up on the nose. So coefficient of moment is measured about the nose. Let's try to look at it on this graph right here. Every time we pitched up, right, a positive number on this side, what happened? There was a negative force. What about every time we pitched down? every time our nose went down. Well, the tail would try to bring it back up. This coefficient of moment would be pointing up. So we can look at this negative thing that goes through the origin ideally, right? This is giving a restoring force. This is kind of what aircraft dynamics are about. How can I have aerodynamic surfaces such that there's a restoring force every time there's a disturbance? So coefficient of moment versus alpha. This is what it's trying to tell us. Let's say, your tail is it's not doing its job too well, right? It's not going through the origin. We can see a period of time where our we're pitching down, but it's still generating a down force. What could you do? Say this is your tail. It's not a good tail. Again, these tails are usually symmetric, right? You could just pitch it. Oh, let's internalize this. Angle of attack is negative, and we're generating a negative force. That means it's generating too much negative coefficient of moment. So we would pitch it up a little bit. And it might go like that. And then we could pitch it down, we can adjust that. So this is what a tail angle of incidence does. I hope you know what what an angle of incidence is. It's just, if my aircraft is literally in a hangar and it's not doing anything, and this is my airfoil on top of it, and there's already an angle of attack given to it, that is your angle of incidence. So tails can also have an angle of incidence, and they can help with this coefficient of moment. Yeah. Maybe I got this backwards, by the way. If it is if your alpha is negative, meaning it is pointing down, and we're still generating down force, yes, then you would probably point it up. I was correct. I'm the GOAT. Why do I even doubt myself? So, um, let's go on and continue with this longitudinal stability because we can get into a very cool topic here, and it will help you understand how your center of gravity and why that really matters so much. Before we get into that, we have to understand what something called the neutral point is. Neutral points. So you have wings and you have a tail, right? And your wings, they generate a force called, lift, and your tails, they generate a pitching moment. So like that guy. And whenever you want to use your elevator to do anything, your aircraft rotates. Ta-da! It's rotating. The point about which it's rotating, right? That is your neutral point. Okay, as you can see, this thing is still following an arc. So my neutral point is probably a little more here. This is in the drawing. Obviously, in real life, aircrafts don't rotate about a drawing. Okay, this still sucks. I'm gonna move it closer to here. Right? Wow, that was me trying to highlight this whole thing. Basically, the point about which this thing rotates is called the neutral point, and the neutral point is your aerodynamic center. So when these aerodynamic forces balance each other out, and whenever you try to pitch with the elevator, the point that it rotates about is your neutral point. Now, your neutral point is somewhere usually in between your wing and your tail, right? Now, let's play a balancing game, right? Also, I mentioned the lifting force earlier. You can kind of ignore that. All I want to say is that the wings generate an aerodynamic force, the tail generate an aerodynamic force, and the sum of that is your aerodynamic center. But for the rest of longitudinal stability, we're going to kind of ignore the wing for now, and we're only going to recognize this aerodynamic center. Let's draw a lever, right? Where many of us are mechanical engineers, levers are very important to us. Obviously, we know with levers, the further something is, you know, this force is greater than this force, and you know, if you have a tiny force here and a massive force here, they can be equal because of torque and because of moment, right? So our wings, our tails, sorry, the tail is what we're here to discuss. Our tails are all the way at the end of our aircraft, right? Let's pretend that these two things are kind of the same thing, but we're not drawing all the other stuff. We're just drawing our important forces for longitudinal stability. What is this fulcrum right here? This fulcrum is our, why did I write that? Our neutral point. I should just write NP, shouldn't I? NP, our neutral point. Why is it our neutral point? Because that's the point about which this whole thing rotates. It's our aerodynamic center, right? So this can be considered our pivoting point. I hope that makes sense. Now we have this tail force right here, right? And it's pushing down. What is on the other side of our neutral point? It is our center of gravity. And this is a big force, right? Obviously, if we want our aircraft to not just immediately tip over and fall this way, we have to put these things at the right place on this beam. What we do is we put this big force closer to the neutral point, and obviously our tail is as far as our tail is. Now, let's imagine you want to use the tail to do something, right? You want to use the tail to pitch up, you want it to pitch down, right? Let's imagine this whole arrow, this center of gravity was even further from the neutral point, right? It was just a little bit further down. That means it would be harder for this tail force to get anything done because there's a larger force on this side. Let's say your center of gravity was very close to the neutral point. That means even a tiny force by the tail, and it's able to tip this giant center of gravity over. And of course, let's move it way further down. Let's say your center of gravity is all the way so close to the nose. Well, no matter what the tail does, this center of gravity is pushing your aircraft down. And finally, let's say your center of gravity does the worst thing ever, is on the other side of your neutral point. That means it doesn't matter what the tail does again. There is no forces on the left side. It's just going to tip over to the back, right? So one thing we can at least recognize is that usually our center of gravity is it's pretty close to the neutral point, but it's slightly ahead of the neutral point. If it's more ahead than it should be, our tail can still work, right? But it's a little nose heavy and it's not as effective as you want it to be. If it's tail heavy, however, it doesn't matter how much the tail does, it can't recover from it because that's just not how a lever works. So you at least, a nose heavy plane might fly poorly, but a tail heavy plane will not fly at all. Now, we talked about wanting to put this thing in the perfect place. If you put it here, it's too close. If you put it here, it's too far. What number are we looking for? Well, the distance between your neutral point right here and your center of gravity is called your static margin. Your static margin is a percentage of your mean aerodynamic chord. So it's just obviously, I hope you watch the other videos. You have your chord length if this is your plane from above. Sometimes, well, usually aircraft should have tapers, and so your mean chord length, which might be somewhere around there, that is, I mean, it would usually almost always be in the center. That's how that works. I mean, not necessarily. You don't have to have a straight taper, right? So your mean aerodynamic chord times your static margin gives you this distance. So, for example, I'm going to actually give you a number right here, which is one of the best rules of thumb. 15% static margin gives you a very, very stable aircraft. If you go 18% static margin, what does that mean? That means, this center of gravity moves a little further away from your neutral point. That means your tail doesn't do as much work. Let's say you go a little lower, let's say you go 13%. That means your plane's going to be a little twitchier, right? Your tail has more authority and it's able to throw that center of gravity around a little faster. And it's able to obviously pitch your whole aircraft. So again, let's go over this. Your beam is your plane, right? Your tail is the force that's causing this whole beam to rotate, right? If your center of gravity is closer to the nose, that means it's harder for it to rotate. If it's closer and closer to the neutral point, it's easier for it to rotate because obviously that's how levers work. Your static margin is the distance between your center of gravity and your neutral point. 15% is a really good number. We use it, depending on the aircraft that you're making. Um, and this number, I'm just rambling. Yeah, 15% is a good number. Your tail won't have too much authority. It'll be stable. It won't twitch, and it won't fall out of control. So these are the things I wanted to discuss in this video. Longitudinal stability, coefficient of moment. I hope you've got that too. The lift formula. You know what? I should go ahead and knock out lateral stability while I'm here. Because I mean, if you're watching this a little bit too much into the future, you might not know what happened, but we had a test flight on a really windy day, and the pilot didn't like the lateral stability of many of the aircrafts anyways. So that's not the best news. So what is lateral stability? Lateral stability, we looked at the plane from the side. Now we're going to look at the plane from the front. It is how stable is it in rolling, right? So in the same way, we're engineers, we can recognize that this is kind of like a beam or even moment of inertia, right? The longer your wing is, the harder it will be because this is your center of rotation. Let's say this is the center of your lifting force. If your wing's smaller, then this is the center of your lifting force. And, it's easier to rotate something with a lower moment of inertia than something with a higher moment of inertia. If you have a glider, right? Gliders have these massive wings. Those things will not roll without permission ever because their moment of inertia is really high. So that is your rolling stability. How can you improve your rolling stability? Well, let's say you have, again, your nose and your wings, and you add a dihedral, right? A dihedral is when your wings are, tilted up like this. What happens when a disturbance occurs and, or a disturbance, or even let's say you roll this way, you roll to the right. Let's say we're looking at our aircraft from behind now. You roll to the right. Well, this wing right here, the right wing, is seeing very good airflow, right? It's literally in line with the wind coming in. Obviously, that's not technically true. That looks like I'm drawing a force down. Say this is the aircraft, this is the wing. This right wing is seeing a lot better airflow. What's going to happen? It's going to generate even more lift. It's going to generate more lift, and it'll cause the aircraft to come back like this. Let's say you were to go to the left. Now the left wing sees a really good airflow, and it generates more lift, and it goes back like this. So this is how a dihedral creates a restorative force in a roll. And so that is lateral stability. Covered lateral stability, static margin, longitudinal stability. What is left to mention? We could mention twists, but that's too much work, or taper ratios. We can talk about that in the XFLR 5 videos. I would go watch those. Some of these topics might still seem a little abstract, right? But if you watch the XFLR 5 videos and when we begin to actually apply it, these things will begin to click into place. I hope something makes sense and I didn't just waste like 30 minutes. So, yeah, see you in the next video.